All right, hello everybody. So this is going to be a different talk to all the ones that we heard in this session previously. So we move now from galaxies and from the interstellar medium and the far infrared and the CO observations to UV and X-rays now, and from galaxies to the nuclei and the active nuclei of some galaxies, the so-called AGN. So I'm going to present new results that we have been doing together with a couple of colleagues in Prague and in Toulouse, Michal Dovzhiak and Elias Kamoun. And this is work that focus on the study of the X-ray emission and optical UV from the center of active galactic nuclei. And I will start with the usual cartoon of how we think an active galactic nucleus may look like. This is the original one. Okay, this is not this is not with the colors, but that's how it was published by Yuri and Padovani. And AGN are fascinating objects. They are the most luminous persistent sources in the universe, and they're extremely variable on all time scales, all wavelengths, and they are ideal laboratories to study, conditions near supermassive black holes, physical conditions, how matter works, how light is emitted, and so on. And the center, right there, the center of those objects lies the supermassive black hole here, and around it there is the disk, the disk of gas. The gas, loses angular momentum, moves inwards, and then it releases gravitational potential energy. Actually, this is the most efficient, mechanism to produce energy in nature. If you leave a particle that comes from infinity and goes down there to the center of this supermassive black hole, if the supermassive black hole is maximally rotating, then you may as well release 40% of the rest mass energy. It's amazingly efficient, the mechanism. And the structure of the disk was studied and was developed in early 70s, and the two major seminal papers are those of Shakur-Shnyai of 1973 and Novikov-Thorne 1973. Again, same year, Novikov-Thorne, gave us the structure of the disk, that is temperature, density, height of the disk, even in the Kerr case, maximally spinning black holes. There is at least one issue with accretion disk, the standard model of accretion disk, and that is that we do know that AGN emit in X-rays. They're very strong X-ray emitters, and here I just show you an example. This is the energy spectrum. Here we have energy on the x-axis, and the y-axis nu f nu, that is power, right? X per second. Right. And you can see most of the power comes here in this part. This is optical, this is UV. And in the X-rays, though, in fact, you can see here, this is soft X-rays, this is harder X-rays, these are 100 keV. In fact, perhaps most of the energy in this object may come actually in the X-rays, not in the so-called big blue bump. So really, there are lots of X-rays coming from these objects. And it's not just nearby Seyfert's. This is NGC 548. I'll come back to that object quite a few times throughout the talk. But you see something similar in distant quasars as well. These are results from the Cosmos survey, the survey with XMM and Chandra. Almost all sources in these X-ray surveys are AGN. And what we plot here is the ratio of the bolometric luminosity over the luminosity in the 2 to 10 keV band. This is X-rays. And you can see that objects that here on the x-axis, this is the accretion rate. Objects with a small accretion rate, they are, quite hard X-ray emitters. This is 10% of the bolometric luminosity will come in this band, the 2 to 10 keV band. And as the accretion rate increases, you have objects where the ratio of the bolometric over the 2 to 10 keV band luminosity is approximately 1% of the, the 2 to 10 keV luminosity is about approximately 1% of the bolometric. But of course, this is 2 to 10 keV band. If you assume that the X-ray energy spectrum, goes from, let's say, 0.1 keV up to 1 MeV with a slope of 2, and there is a high energy cutoff at around 300 keV, then these objects, most of the bolometric luminosity will be emitted in X-rays, while these ones, the ones that show this ratio to be about 1%, well, if you consider the full luminosity, then, the X-ray, in the X-ray band, you may have up to 30% of the bolometric luminosity. So really, X-rays are strong X-ray emitters. And of course, standard activation disk models cannot explain X-ray emission because the temperature of the disk, even, near the center, very close to the supermassive black hole, close to the innermost stable orbit, temperature cannot reach 100,000 K for the masses of those black holes there, even if the objects, accrete close to them. So there must be another component there that emits X-rays, and there have been quite a few suggestions, like perhaps in the inner part of the disk, just before the ISCO, there is a hot plasma emitting trace, or perhaps due to mechanical connection, you have these active regions where you actually hit electrons up to 10 to the 8, 10 to the 9 K, and then they subsequently, scatter photons that are emitted from the disk, to, photons, optical UV photons to X-rays, or perhaps the X-ray source is there at the axis of symmetry of your system. This is the so-called lamppost geometry. Here is the patchy corona, or this one is the inner hot corona. Whatever, the X-rays must come really from the center of the system, because we know from micron lensing observations of distant quasars that the size of the X-ray corona cannot probably be larger than about 20 RG or so. So we're talking really about, physical processes that take place at the right there at the center of these objects. And we also have another very interesting observational fact. And what I'm showing here is the energy spectrum X-rays now, just X-rays from 3 keV up to 60, 70 keV of this nearby Seyfert NGC 1365. These are observations with New Star. These are observations with XMM Newton. Well, of course, XMM Newton goes up to about 10 keV or so. What you can see here is a very strong emission, iron line from iron, at about 6.4 keV, but you also see a very, very prominent asymmetric profile towards lower energies, and you also see this very, very, very strong component on top of the continuum. This is the so-called Compton Hump, and this asymmetry in the profile of the iron line tells you that most probably the X-rays shine the inner disk, because all these are the effects of the GR effects that take place very, very, very close to the supermassive black hole. We believe that the X-rays shine the disk absorbs energy, but also reprocesses those X-rays and re-emits them again in the X-ray band. And actually this emission line and this Compton Hump are the signs of X-ray reprocessed emission from the disk, but due to the shape, this extreme shape, we believe that this is a reprocessed emission from the inner disk, where the material, rotates around the black hole with speeds that are close to the speed of light. So we do have information, we do have indications from observations that X-rays, they really emitted very close to the center, and they probably also shine the inner disk. But of course, if that's the case, then as I said, part of the X-rays will be absorbed. Some of them will be reflected, but because most of the X-rays will be absorbed, this is an extra source of heating for the accretion disk. So the disk temperature will rise, right? Okay, and so will the UV and optical emission. What's even more interesting is that the X-rays are variable. I mean, nature and X-rays are always variable. And of course, the reprocessed UV and optical emission should also be variable. And what's even more important, it should also be delayed. It will take time, for X-rays to leave the source, reach the disk, get reprocessed, and then re-emitted for the observer to see these reprocessed emission. So, and these delays, of course, should increase, as you go to longer wavelengths. You have X-rays, disk, gets heated, it starts emitting UV from the set, and optical, infrared further out, and so on. So we do, if that's the case, if X-rays do shine the disk, we do expect to see all these effects, and this is actually the so-called disk thermal reverberation process. And in fact, we do see that. And I mean, even at the beginning of the 1990s, when we first observed these asymmetric iron line profiles and so on, people went out there, they used this is IUE, the International Ultra Violet Explorer. It was observing in extreme UV wavelengths, 1,380, 1,840, 2,370 angstroms. And Ginga was a Japanese X-ray satellite. So these two satellites were monitored, NGC 5548, April and May 1990. And then 1992, the results came out. I remember, there was a big fuss back then. You can see the UV being variable, up and then going down, and broadly following the X-rays. Okay, forget about this very annoying point up here, but you can see the X-rays doing the same thing, and the UV and optical following with a delay. I mean, you can see here is the maximum is delayed and so on with respect to X-rays. Fast forward now, approximately 25 years later, and this is the same object, NGC 5548, in 2014, February to June, and you can see here, this is Swift observations, this is X-rays, this is HST observations, and these are the UVOT monitoring, UV and optical monitoring in Swift. But you can see at the same time, it was not just the HST and the Swift, but there was all sorts, so many optical telescopes all around the world, observing the same object, the same active nucleus. And now I think you can even by eye see very, very clearly that UV and optical are variable. And at the same time, I mean, you can see this is HST, and look here, at the, this is 2,250 approximately angstroms, and look here, right? Okay, this is the U band. You can see the peak of the emission, is clearly delayed, with respect to the UV. It's not so clear with X-rays, what's happening with X-rays, but clearly you see delays in the UV and optical, and these delays, increase as the wavelength increases as well. And well, at the beginning, people thought that these delays are just, they measure light travel time between X-rays and the place on the disk where, most of the emission that you observe comes from. So suppose you have the V-band filter, you have 5,100 approximately angstroms you observe, and you say, all right, okay, most of the light that I'm going to see at this wavelength comes from this part of the disk where the temperature is such so that the Wien law will be fulfilled, right? Okay, so you have wavelength and you say, all right, I need that kind of temperature to observe at that wavelength, right? So the delay that I see now, the delay that I observe is more or less, the time it takes for the light from X-rays to come at this part of the disk, heat it up, and then, I will see it if I am in this direction. Now, according to the standard disk model, the temperature at this distance from the center will depend on the distance. The further you go out, the cooler the disk is going to be, but it also depends on the black hole mass and on the accretion rate. And of course, now, if you assume that this distance is given by your light travel time, and you put there the delay that you see, then of course, the temperature because you observe at that particular wavelength, and you can measure, for example, the accretion rate that you need to hit the disk at that kind of temperatures, at that kind of distance from here. And people had done this modeling, and it's not just with 548, quite a few more sources I'll show you later. And what they saw is what I show you here is, wavelengths here, and on the y-axis, time delays between, let's say, okay, this is 6,000 angstrom. So time delay of the variations that I'm going to see at this wavelength with respect, they took as a reference wavelength here, 1,300, approximately 1,300 angstrom. That was one of the bands that they were observing with HST. So you can see that the delays are of the order of 3 days. The order of days. The variations are delayed, but the delays seem to be quite large. So this disk seems to be quite hot at very large distances from the center. And in order to achieve that, you have to feed the disk with a high accretion rate. So they could get, you know, a reasonably good agreement with the model, but only if the accretion rates were of the order of Eddington limit or 10 times Eddington, you know, somewhere there. And that was a problem because when they would observe the object itself, the luminosity of the object was not that great. You know, you would assume that the disk, you know, accretes at this really high accretion rate, but the nucleus didn't seem to be that bright. So that was a problem, right? And I'm just showing here, you know, from a paper by Schiantonucci in 2015, saying that this is incredibly important, you know, this discrepancy, because it means that the radiation does not come from the region where the energy is released, right? Okay, the disk seems to be very, very hot, very far away, while most of the energy comes from the inner part, right? So, you know, he says that I conclude from this that we know next to nothing about the fundamental physics of radiation from AGN. That's a very strong argument, but indeed it is an issue. However, if indeed you have X-rays illuminating your disk, all right, okay, these delays are not just simply, you know, a light travel time. No way, no. You know, when you eliminate the disk and you are observing at a particular wavelength, you know, and this flux that is emitted at this particular wavelength is variable, right? Okay, then what you see is, you know, is caused by the emission of a standard disk. You know, material, you know, comes in, hits the disk, following, you know, temperature profiles, let's say, of Novikov Thorne, plus the extra heat that the X-rays give you. So here are the X-rays in the past, you know, they hit the disk. So what you see now is, you know, what kind of heat you got from the X-rays that were emitted one day, you know, ago, or 5 days, or 10 days ago, or whatever, depending on how your disk, you know, how your disk responds to X-rays. This is the response function of the accretion disk, and I'm going to discuss about that later on. Basically, your cross-correlation functions measures the centroid of this function. All right, you have to find this function, and you have to measure the width of this function. Your delay is actually proportional to the width of that function, okay? This is the centroid of this particular function. It depends on the width of that function. So that's what we try to do. We try to see what's wrong, you know, why, you know, X-ray illumination can explain quite a lot of the X-ray data that we see, but it doesn't seem to agree with what we see in the UV and optical delay. So what we did is we assumed, you know, a lamppost, a corona that is there on the axis of symmetry, illuminates the disk, and then, you know, the observer sees the emission from the disk. The disk is Keplerian. We assume Novikov Thorne, you know, all the relativistic effects. The X-ray source in its rest frame emits isotropical, but not, you know, what the observer is going to see. The observer is going to see different things depending on GR, you know, how close that is to the hole. And we studied and we tried to determine really accurately the response of the disk to an X-ray flash. So we assume that the X-ray source is here, and all of a sudden just, you know, shines the disk with a burst of radiation. And what we do is we come to each radius of the disk. We actually estimate how much flux is absorbed. First of all, how much flux is incident on the disk, and then how much of that will be reflected, how much of that will be absorbed, and then we go to the observer's frame, and we take into account all relativistic effects, because of course the observer is not going to see this ring at the same time. The observer is going to see ellipses, you know, at each time. All right, okay, different parts of the disk will be observed by the disk at different times, and knowing how much flux is absorbed, we know the new temperature of the disk, and then what we do is we subtract from the extra flux that the disk is emitting the flux that is due just to the standard disk model, and this excess flux at each time, as observed by the observer, right? Okay, this exactly is the response function of the disk at each particular wavelength. This is, of course, I explained all this very, very quickly. If you like, we can discuss that later, but it can be done, all right? Okay, it can be done by taking into account all the relativistic effects. And of course, if the X-ray, if the response is defined in this way, then what you observe at each time is indeed, what the disk emits, plus this response times, all the past, X-ray that was emitted, in the past. It's how X-rays are going to affect what you see now depends on the response of your disk. And here are two examples of these responses: response of accretion disk at the extreme UV and in the I band. And what you see is that as you shine the X-rays, you will start seeing the inner part of the disk. This inner part is very, very hot. Of course, it emits UV, but of course, it emits in the I band as well. Yes, the size is small, but the temperature is so high so that immediately you will see the response of the disk in the I band to actually, rise up. What happens is that as this X-ray flash, starts expanding, you start now seeing the outer part of the disk, which are not so hot anymore. So now the response of your disk in the UV band starts declining very, very fast. But of course, the outer part of the disk still emits in the I band. So it's the fact that the response of the disk is so much broader in the I band that is going to make your time delays to increase with wavelength as you go to the higher, larger wavelengths, right? The response in the UV, the response of your disk is narrow, but as the wavelength increases, the response of the disk increases and increases and increases. So what we did is we computed model response functions, and then we computed their centroids. And then what we did is we found a relation between those time delays and the height of the source from the disk, the accretion rate, the X-ray luminosity. It's a very complicated function. That is true. The time lags are not simple functions of the height of m dot and Lx. The system is complicated, but it can be found. Those functions can be determined, and we determine them. They're different for spin 0, and they're different for this is spin 0 case, this is spin 1 case. But of course, then when you fit the data with the proper time lag models, then of course you get very, very good fit. There have been now quite a few sources, quite a few nearby AGN where we have studied their their time lags as a function of wavelength. There it is. These are delays in days. These are wavelengths for many sources. For 6 sources in this case. This is NGC55, brilliant fit, both for spin 0 and spin 1. But what's even important is not that we fit these time lags very, very well. What I show here are these 6 sources, the name of the sources, Markarian 142, Markarian 509, and so on. And here is the accretion rate as estimated from our fits to the data. And the red points here show you the best fit results in the case of maximally spinning black holes, Kerr, right? Okay, maximally spinning. And the blue points show you the m dot in the case of Schwarzschild black holes, non-rotating black holes. And the black one are estimates of the m dot from literature. Look at this point here, Markarian 142. Based on their luminosity, people think that it's almost Eddington. Our fitting, completely different approach, indeed shows very high accretion rates in both cases. It's amazing. We were really happy and very surprised that our estimates are so much in agreement with the luminosity of these objects, how they look, right? Look at NGC 5548. All right, okay. This is, people thought that the time lags could be explained if the source was emitting at Eddington limit. No, we can get a very good fit when the m dot is approximately as people thought it is, a few times, 0.05 of the Eddington. In fact, we find a very good agreement of the, between our estimate of the accretion rate and the literature values if the source is maximally spinning. Because in the case of Schwarzschild, our estimate of m dot is too small. The object, NGC 55, should actually look much fainter than what it looks if indeed the source was a Schwarzschild, if the black hole was a Schwarzschild black hole. So basically, there is nothing wrong with the disk, the standard disk model. It's not that the disks are hotter or whatever, that there is any problem. No, it
Just
could.
3 minutes.
Yes, fine. I'm almost done. It's just that the X-ray source is located further away from the disk, right? Okay, we get a good fit when the heights are of that order, but there is nothing wrong. And I will just finish with what, because this is an ongoing work. And of course, you know, we have this wonderful data. And yes, you can estimate the variability, but also you can simply get the mean. And you can get a beautiful energy spectrum. Can you fit it? Can you fit now the energy spectrum of the source? And actually, the code now is much more developed. Now we conserve energy, we conserve photon number due to Comptonizing process and so on. Anyway, the point is that yes, we can fit the average energy spectrum of the source. So this is again HC548. This is optical. This is HST, and the UVOT on Swift, and this is the X-rays. And average energy spectrum of the source over months, right? And this is the intrinsic spectrum of the source, right? Okay. Exactly as we got from the time lags, and an accretion rate of the order of 0.1 of Eddington, but a spin larger than 0.8. This is a supermassive black hole, very, very close to maximally spinning, right? Okay, with an X-ray source at about, you know, between 3 and 40 RG, and most of the X-rays, most of the bolometric luminosity comes in the X-rays. The ratio Lx over L ball is around 0.5, exactly as people had observed in the past. So I'm going to stop here and say that this is a hot subject. There has been a vast observational effort the last 10 years or so. Many sources have been monitored for months, lots of ground-based telescopes, lots of time with satellites, all right, again, trying to understand how the X-rays, UV and optical, you know, vary together. And we just find that standard models of accretion disks are perfectly fine. And we can get actually important information about the geometry between X-rays and the accretion disk, you know, height of the X-ray source, accretion rate, also whether the source is, you know, the spin of the supermassive black hole there, and so on. So I'm going to stop here, and thank you very much for your attention.
Thank you very much, Joseph. We have time for a couple of questions. Adonis, I think you can unmute. Yes.
Yeah, hi, Sifis. So I have two questions for you. The first one, I was a bit surprised to see in your transfer function a dependence on Lx. I can understand the dependence of black hole. It was not clear to me why there was a dependence on Lx. How physically, what does that mean? And the second question is, all that, I mean, prediction also is that the X-rays should come first. Variability of X-rays is first, and in that source that you showed, at least the one that you showed, this is a little bit not easily seen from the data, at least to the eye.
Absolutely. Okay. So first, about the first question, you know, for a given m dot black hole mass, everything, if the X-ray source is more luminous, this is going to be broader. You will get emission from the outer part of the disk because there will be more X-ray flux absorbed. Right? So it's all about the width, right? Okay. So the width depends on X-rays.
Okay.
Right. Okay. So, but yes, this is a major issue. I think we can fit more or less everything. We are doing now even alpha OX, and results are fine. But I agree with you. So there are your X-rays, and this is actually I-band, NGC548. So someone will say no way, and yet, if you take this one, if you take this one, but mind you, this is 10 days in width, right? So if you take this, and for each point here, you go and you convolve 10 days of these X-rays with your response, this is what you get. You see?
Help me understand a little bit.
Prediction. This is
that?
observations.
Yeah.
And this is what I predict if I use the
I see what you're saying.
and mind you now, I have issues because I need to know exactly the distance to the object, because now this is amplitude. I have to know X per second of the source. So here, these kind of uncertainties are tiny, really. You know, if the source, because I'm using, you know, cosmology, you know, I'm taking redshift, this is, we don't know the distance, you know, because, you know, with the CFITs or whatever, right? So now I will probably not be able to match it exactly because there are now so many details, but look what, you know, the transfer functions that I get, this is what they predict with using the observations, right? We now use the observed X-rays to predict. This is a major project that will take time. This is not, but this will be the ultimate. And in fact, it's very interesting because in this way, if we take out the reverberation signal, we will see the disk itself, what it does. Is it variable on its own, right?
Yeah, okay,
so, yeah. I agree. It doesn't look promising that this one will cause this. These are observations, right? Both of them.
Yeah.
Yes, if you take the transfer function and you convolve this with the transfer function, this is what you get here.
Super. Okay.
So
thanks.
It seems to be okay.
Yeah, yeah.
I think, do you want to ask further questions? Gina has...
Oh, sure. Yeah. Hi, Gina. Hi.
Hi. So I'm wondering, can you apply the same analysis for X-ray binaries? And would you be able to constrain to compare spin estimates from this analysis with other spin estimates?
Well, yeah, right. You can do it, but things are different in X-ray binaries. I mean, the disk itself emits in X-rays because it's much hotter. And you cannot really observe easily UV and optical because you have the optical star there. So, you know, you will get the accretion disk, which will be in X-rays, and there, to estimate the reflection properly in this kind of disk. The reflection here is taken from studies, state of the art, but these studies are for particular disks, particular densities and particular temperatures. When you have your disk with much higher temperature, ionization state is completely different. That affects enormously the part of the X-rays that the disk reflects, which means the part that it absorbs. So it's not going to be so easy. It's not straightforward to go from AGN to the binaries. So we haven't even thought of that yet.
I see. Thanks.